All right, welcome to the Chapter 13 Part 1 video. This video will cover 13.1, 13.2, and 13.3, where we'll be talking about probability. So 13.1, we're talking about the difference between experimental and theoretical probability. And we did an activity during the first part of class today that you will need to refer to through this notes. I can't fill it in during the video because I don't have those numbers yet because this is pre-recorded. Okay, so the first thing that we're going to look at is our objective, which is to understand how to calculate experimental and theoretical probability. And part of that is knowing the difference between those two types of probability. So we're going to start by thinking about something that probably intuitively you could already answer these questions. So consider the likelihood of each event. Do you think one is more likely to occur? Which one, or do they have the same chance of occurring? Starting with flipping a coin. So a coin has two sides. We call one side head, one side tails. So if we flip a coin, are we more likely to flip heads or tails? When we're talking about coins, unless it specifies that it's a weighted coin, we will always assume that it's a fair coin. And if it's a fair coin, that means it's really a 50-50 chance, okay? And so we are equally likely to flip heads or tails. In our second case here, snow in Alaska versus snow in the Sahara Desert. Well, we know that Alaska is cold and deserts are hot. And so snow happens when it's cold. So it's more likely to snow in Alaska. In our third case here, rolling an odd number on a die versus rolling a 3 on a die. Now, die is singular, dice is plural. So this says we're rolling only 1, and we want to know, are we more likely to get an odd number or 3? Well, 3 is an odd number, but 1 and 5 are also odd numbers. So there are 3 different numbers that we could roll in order to satisfy this first case, and only 1 number that we can roll to satisfy the second case. So we are more likely to roll an odd number, which does include 3, but it also includes 1 or 5. Okay, so what we're going to look at first is how do we calculate these probabilities? How are we going to be able to tell, and how do we know when it's experimental versus theoretical? So let's look at our definition of probability. Probability is the likelihood an event will occur, and it's always going to be a value between 0 and 1. Those values can be represented as fractions, decimals, or percentages. If it doesn't specify, you can use any of the 3, but your default should be fraction. We denote probability as P of an event, and sometimes we can call that event A and B if we're talking about multiple events. So if we're calling event A and we want to know the probability of that occurring, we would say P of A. And the way we calculate that is the number of possible outcomes that would give us a success. So if it satisfies our condition, out of the total number of outcomes that we could have for that situation. So another way that I like to remember this is want over all. Okay, and we'll practice looking at how do we set up those fractions. And that set of all possible outcomes is called the sample space. So for example, when I'm flipping a coin, my sample space is heads or tails because those are all of my possible outcomes. So when we're looking at another example here, the probability of rolling 3 on a regular or a fair 6-sided die, we can denote it as the probability of what we want, so probability of 3. And we want to know how many times will we, or how many chances do we have to roll a 3, and how many options are there for our possible outcomes. Okay, so we want to know rolling a 3 versus all possibilities. Well, there's only one side of the die that has a 3, so there's only one outcome that gives us a success, but there are 6 sides of the die, and therefore there are 6 possible outcomes. So if we're looking at a die, right, we have 1, 2, 4, and so if I look at all of the sides of a die, my options are 1, 2, 3, 4, 5, or 6. Now, if I want to roll a 3, only one of those options would count as a success, but I have 6 total possible outcomes. And that's where we get this fraction. Now, if you put this into your calculator and you simplify it into a decimal, we can round it to 0.17. And then turning that decimal into a percent, remember to turn something into a percent, we move the decimal place twice, dividing it by 100. 17 divided by 100 is 0.17. So percent means divided by 100. So moving the decimal place twice. If you need more review of how to calculate from a fraction to a decimal or to a percent, that's something that we can definitely talk about in office hours. So let's take a look at the next little part here where I want you to make a prediction. Okay, if you flip a coin 12 times, how many times would you expect to get heads? Okay, so I would like you to make a prediction. And then if you roll a fair 6-sided die 12 times, how many times do you expect to roll a 4? Okay, and now this is the experiment that we did together during the first part of class. So I cannot fill this part of the notes out. However, this is the activity where you did these experiments. So you'll put your results here. And then the class results are on that spreadsheet. And so you'll fill in the class results here. All right, looking at the next page. So hopefully you've finished filling out that experiment that we did together. So we want to define theoretical probability and experimental probability. So theoretical probability describes the likelihood of an event or a probability based on logic. Okay, and what this is if we had an infinite amount of time to do an infinite number of experiments, then this is the result that we would expect. So this is based on an infinite trial, which we could never actually complete, which is why it's called theoretical probability. And then experimental probability is the likelihood of event based on a trial. So this is what we have actually computed based on an experiment. Okay, so let's calculate some theoretical probabilities. So theoretically, if I wanted to know the probability that a coin will land on tails, then I want to know how many times, how many number of outcomes give me tails, and how many number of outcomes are possible. Well, a coin, there's 2 possible outcomes, heads or tails. One of those is tails out of the 2 possible outcomes. And so our theoretical probability is 1/2, which we could also write as 0.5, which we can also write as 50%. Similarly, if we're looking at the probability of heads, we have 2 possible outcomes for flipping a coin, heads or tails. Our event that we want to look at now is how many of those is heads and how many are possible. So how many of those outcomes would give us heads? 1. How many outcomes are possible? 2. So this is an equal likelihood, tails versus heads. If we convert that to a decimal, it's 0.5. If we convert it to a percent, it's 50%. Now let's look at the probability of rolling a 4. So our outcomes, our possible outcomes, 1, 2, 3, 4, 5, or 6 from a 6-sided number cube or a 6-sided die. What is the event we're looking at? We want to know how many of those outcomes give me a 4. And the denominator is always how many outcomes are possible. So how many of these outcomes give me a 4? Just the 1. How many are possible? 6 are possible. Now this one, when we calculate, we will have to round. So these ones were really equal. because 1/2 is equal to 0.5, but the little squiggly equal sign means that it's an approximation, it's rounded. So 1/6 is approximately 0.17, which we can then write as 17%. And then the last theoretical probability we're going to look at for this section is the probability that we will roll an even number. So we have 1, 2, 3, 4, 5, and 6 are our possible outcomes. Remember, we call that our sample space. So we want to know how many of those are even and how many are they all together. Even numbers 2, 4, and 6. So I have 3 possible outcomes that I want out of 6 total possible outcomes. 3 divided by 6 is equal to 1/2, which is equal to 0.5, which is equal to 50%. Now for the experimental probability, you'll need to use the numbers that we were given from that spreadsheet. So from the previous page that you just wrote down, and you're gonna do the same thing. What are my possible outcomes? And those should be the same, okay? And how many events, how many were actually, how many happened? So how many times did someone in the class flip tails? And how many coin flips were there for the class? How many coin flips were heads? And how many total coin flips were there for the class? So those two denominators should be the same. How many people rolled a 4 and how many total dice rolls were there? How many people rolled an even number and how many total dice rolls were there? Once you finish filling all of those out, the next section is for creating kind of your own definition in order to define probability, okay? So again, this is something that based on what we've talked about so far, what is your understanding of probability? So I don't want you to copy the definitions from above. I'd like you to write it in your own words, okay? I'm not going to give you a definition right now because I don't want you to give my definition. I'd like you to come up with your own understanding of what is probability and an example of how to calculate basic probability. Now you can do an example using a die or using a coin, but you could do something else. You could do the probability of, for example, choosing a letter from the alphabet or choosing a 1-digit number or really anything that you kind of can make sense of. Okay, so this is an opportunity for you to think through what we've talked about so far. And then we're going to do a couple of actually example calculations. So underneath that, we have an example here. A quality control inspector samples 500 LCD monitors and finds defects in 3 of them. What is the experimental probability that a monitor selected at random will have a defect? So again, we're looking at event over total. We want to know the probability of having a defect. So that's going to be the number of defects divided by the number of all possible outcomes. So if we look back up at the problem, there are 500 monitors and there are defects in 3 of them. So how many have defects? 3. How many monitors are there altogether? 500. And so our experimental probability is 3 over 500. We should ask ourselves, can it be simplified? Well, 3 does not go into 500 evenly, and so this is the simplified fraction. If I wanted to write this in a decimal, we can write it as 0.006. And if we want to write this as a percent, move the decimal over twice, is 0.6%. Okay, the second part is then saying, so we tested 500 monitors, but if we are manufacturing, so if the company manufactures 15,240 monitors, how many are likely to have a defect? So we took this small sample and we're going to then determine how many of the monitors that we manufactured are likely to have a defect, okay? So we're using that probability in order to find out a much larger sample size. And the way we do this is we still set up the fraction the same way. It's events over total, but we would expect the probability to be the same because it was the same manufacturing process for all of these TVs. So we take our probability from above, 3 over 500, and we say, well, what about how many defects would there be? I don't know, for all of these monitors. So our unknown is the number of defects of all 15,240 monitors. So we're setting it up the same way. How many defects over all of the monitors? How many defects over all of the monitors? And now we need to solve for x. Well, to solve for x, I want to multiply both sides by 15,240 so that I can get x equals, and I would absolutely use a calculator for this part, 3 times 15,240 divided by 500, which gives us 91.44. Now I can't have 91.44 monitors, and so we're going to round to the nearest whole number. And so we approximate that to be 91 monitors with a defect. Now, how come we got a number bigger than 1? Well, this 91 is not a probability, right? The 91 represents the number of monitors that had a defect. The probability for this problem was still that 3 over 500. Let's take a look at another. On this page, our next example is looking at theoretical probability. So we saw an example with experimental probability, and now we're going to do some examples with theoretical probability. So suppose you roll a fair 6-sided die, or also called a number cube. What is the theoretical probability that it lands on a 5? This is very similar to the question we were asking before. So probability of 5 equals how many ways can we roll a 5, and what are our total possible outcomes? This is the sample space. So if I roll a die, what are my options? 1, 2, 3, 4, 5, or 6 are my options. How many of those are 5? 1 is 5, and 6 possible. So this is my probability, 1 over 6. Again, we could estimate that as 0.17 or 17%, depending on how it asks for the results. Usually it will ask for a fraction. Okay, what is the theoretical probability that it lands on an odd number? So now we want to know what is the chance of an odd number. So we need to know how many of them are odd and how many of them are possible. Well, how many of these numbers are odd? 1, 3, and 5 are odd. So we have 3 chances of rolling an odd number out of 6 numbers that can be rolled, which is 1/2, or 0.5, or 50%. Okay, and what is the theoretical probability that it lands on a number greater than 4? So here's a question, is 4 greater than 4? No. So 4 is not part of our sample space of a success. So we want to know probability greater than 4. How many are greater than 4, and how many are there total? Well, 4 is not greater than 4, so there's just 5 and 6. So 2 of them are greater than 4 out of 6 possible, simplifies to 1/3, which we can estimate to be 0.33 or 33%. Let's look at the second example. Angel has a bag of marbles. The bag has 4 white marbles, 4 black marbles, and 2 striped marbles. There's an equal chance of choosing each marble. What is the theoretical probability that Angel will choose a striped, this should be marble? Okay, well, we had 4 white marbles. I'm going to write this as 4 W's. 4 white marbles, 4 black marbles, and 2 striped marbles. Okay, we want to know the probability of striped. So we need to know how many are striped and how many are there altogether. Okay, well, there are 2 striped marbles and 4, 8, 9, 10. 10 marbles altogether, giving us a probability of 1/5, or 0.2, or 20%. What is the theoretical probability that he chooses a black or a striped ball? So now it could be black or striped. So we want to know how many of them are black or striped and how many of them are there altogether. Well, a white marble is not black or striped. A black marble is black or striped, and a striped marble is black or striped. So we're counting all of the black marbles and all of the striped marbles. So 1, 2, 3, 4, 5, 6 out of 10. Remember to simplify. This is 3/5, which is 0.6, or 60%. Okay, let's take a look at our next example, example 3. 138 students at OLP and Saints participate in clubs are listed below. Fill in the missing information in the table. Okay, so we need to fill in the numbers, and we know their totals, right? We know that there are a total of 138 students. So if we look at this, 25, 20, 40, what number needs to be here to add up to 138? Well, I can do 138 minus 40, 60, 85, right? So I know 85 students are freshmen, sophomores, or juniors, so how many are seniors? If I do 138 minus 85, we get 53. And of course, you can use your calculator for that if you need one, right? How many are boys? Well, we know that 74 total are boys. So we have 25 and 24 is 49, plus 15 more is 64. So 74 minus 64 is 10 sophomore boys. You can also do it by looking at the total number of sophomores. Total is 20 sophomores, 10 of them were girls, then 10 must be boys. So 40 of the juniors, 24 are boys, how many are girls? 40 minus 24 is 16. Okay, my pencil broke, so I have a new pencil. And then our total number we can add across here, or we can subtract, right? If 74 are boys, how many are girls? And so either way, you should get 64 total girls. And now we want to find the theoretical probability that a senior is randomly selected. So we want to know, what is the probability of being a senior? Well, seniors, what's the group that we're selecting from? We're selecting from all of the students. So how many seniors are there? So we look at the table and we say, here are the seniors. How many seniors are there? Not senior boys versus senior girls, but seniors total, right? So there are 53 seniors out of 138 students. Into the calculator, and this estimates to be about 0.38, or 38%. Okay, so fraction, decimal, percent. And then our last example here on this page, use the diagram to answer the questions below. So this is rolling a die, okay? And these are the total outcomes for rolling the first die and a second die. So this is the results from rolling 2 dice. What is the theoretical probability that the sum of the 2 cubes is 7? So we want to say, okay, 1 plus 1 is 2, 3, 3 and 1 is 4, 5, 6, 7. That one has a sum of 7. 3, 4, 5, 6, sum of 7. 4, 5, 6, sum of 7. 8, 9, right? So if you notice, all of these that add up to 7 are creating a diagonal here. So how many of them are there? So the number that sum to 7 And the number of all of them, well, 1, 2, 3, 4, 5, 6 of them add up to 7. How many are there total? This is a 6 by 6 grid. 6 by 6 is 36. So there are 36 total possible outcomes, which is 1 over 6 if we simplify it, approximate to 0.17, or 17%. So notice we'll see a lot of the same numbers come up as we're using the same devices. So for a die or dice, this probability of 1/6 comes up pretty frequently. Okay, let's take a look at the next page. On this next page, we're looking at example 5, which uses a standard deck of cards. If you're not familiar with a standard deck of cards, this diagram shows you all of the possible cards in a standard deck. So there are 52 total cards, 4 suits. This is called clubs, spades, hearts, and diamonds. These are black suits, and these are red suits. Okay, my printer doesn't print in color, but if you're looking at the original PDF, you can see that these are black cards and these are red cards because of the color they're printed in. Okay, the ace is not considered a face card unless otherwise stated, and it's also not given a value of 1. So the ace can play different roles in the deck, but we won't call an ace a face card unless it specifies. So our face cards are the ones that actually have faces on them. That's the jack, the queen, and the king. And so we want to know, what is the probability of selecting a face card? So probability of face. So we want to know how many face cards are there out of all of the cards. So we have 3, 6, 9, 12 face cards out of the whole 52 card deck, which simplifies to 3 over 13, which we can then calculate to be 0.23 or 23%. What is the probability of selecting a hearts card? Well, if we look at these hearts, we can count them. So there's 10, 11, 12, 13. So probability of hearts, number of hearts overall. There are 13 hard cards out of the 52 card deck, which simplifies to 1/4, or 0.25, or 25%. So some of these fractions you can simplify in your head. Otherwise, you can use your calculator. If you want some additional instruction on how to do these calculations on your calculator, we can go over that during the second part of class today. Okay, example 3, or question 3. What is the probability of selecting a red queen? So if we look at our queens, these two are black queens, these two are red queens. So probability of red queen. So we want to know how many of them are red queens out of all of them. We have 2 red queens out of the 52 card deck, which is 1 over 26, which is 0.38 or 38%. And what is the probability of selecting a 7 card? Well, there are 4 sevens. Probability of 7, number of sevens overall, 4 out of 52, which simplifies to 1 over 13. 1 over 13 equals 0.077. I believe that's an estimate, which is 7.7%. Okay, so that's finding probability from a deck of cards. What if, instead of looking for the probability of something to happen, we're looking for the probability of something not to happen? That's called the complement probability. So instead of saying, what happens if I draw a 7, the question could be, what's the probability that I'm not going to draw a 7? Okay, and those two things have to add up to 100%, or 1, because the probability that something will happen and won't happen are complementary. It's either going to happen or not happen. So together, there's a 100% chance that something either will or won't happen. So we can then subtract the probability of an event happening to get this equation. the probability that an event won't happen equals 1 minus the probability that the event will happen. Okay? Another way of writing this not is a little tilde. So we can say the probability of not A equals 1 minus the probability of A. So the diagram didn't print here. So I'm going to just copy it down real quick off camera. Okay, so hopefully you have the image. It's on the original PDF if you wanted to refer to the actual image. We want to find the probability of it not raining on Friday. So there's a 5% chance that it will rain on Friday. Probability of not rain is 1 minus the probability of rain. So we have 1 minus, what's the chance that it rains on Friday is 5%, which is 0.05. 1 minus 0.05 is 0.95, or 95% chance of not raining on Friday. 5% chance it will, 95% chance it won't. Then what is the probability of it not raining on Sunday? Well, the probability of not raining is 1 minus the probability of it raining. 1 minus, on Sunday is 80%, which is 0.80. 1 minus 0.80 is 0.20, or 20%. Notice that they add up to 100% in both cases. Okay, an example 2, Sarah has the day off from work. She either wants to go see a movie, to the beach, or to stay home. The probability that she will see a movie is 35%. The probability that she will go to the beach is 52%. What is the probability that she will not go to the beach? So again, probability of not going to the beach is 1 minus the probability of going to the beach. Going to the beach is 52%, which is 0.52. So 1 minus 0.52 equals 0.48, or 48%. What is the probability that she will stay home? Well, probability of staying home is the probability that she will not go to the movie and she will not go to the beach. So the probability of staying home is 1 minus the movie and the beach. So the movie is 0.35, and also minus the beach, 0.52. And so we get 0.13, or 13% chance she stays home. If I add up the movie, the beach, and staying home, it should add up to 100%. All right, number 3, Chris has 5 purple marbles, 4 yellow marbles, and 3 black marbles. His monkey came along and batted 1 marble under the seat. Okay, I'm gonna, similar to before, represent each of the marbles with a letter. What is the probability that the monkey batted a yellow marble? So probability of yellow, number of yellow over all, 4 over 5, and 4 is 9, and 3 is 12, which is 1/3, or 0.33, or 33%. What is the probability that it is not a purple marble? Probability of not purple. So we want to know the number of not purple over all. Well, 5 of them are purple, so 4 and 3 is 7 are not purple over all 12. The other way we can do this is we can say how many are purple and subtract that from 1. So 1 minus the number of purple over all, which is 1, minus 5 over 12, which is 7/12. So notice you'll get the same answer either way. What is the probability that is not a black marble? Similar to the one before, there's two ways we can do this. Probability of not a black marble. I can count everything except for the black ones. So 4 and 5 is 9 over 12. Or I can say that's the same as 1 minus the black ones over 12. 1 minus 3 twelfths, 12 twelfths minus 3 twelfths is 9 twelfths. Either way, that has to be simplified. 9 twelfths simplifies to 3 fourths, or 0.75, or 75%, depending on which format you want to write it in. Okay, that's the end of section 1. We're going to keep going on to section 2. All right, 13.2. So we're going to keep going. We're doing 3 sections today. So our objective for this section is to make use of a frequency table and probability distribution. So first we have to know what the heck are a frequency table and probability distributions. So we're going to start with a frequency table. A frequency table is a data display that shows how often an item appears in a category. Frequency is just another way of talking about experimental probability. Okay, we can talk about relative frequency, the relative frequency, aka experimental probability, is the ratio of the frequency of the category to the total. So category over all, want over all, okay? For example, the results of a student survey in music preferences is organized below. What is the relative frequency of the preference for rock music? Okay, so what we want is we want the number of rock over all. Okay, so rock is 10 divided by all. 10 plus 7 plus 8 plus 5 plus 6 plus 4. So that's 10 over 40, which is 1/4, or 0.25, or 25%. Okay, so what is the relative frequency for classical music? So I'm going to move this down here. Classical music is 5. We already know that the total is 40. We don't have to calculate that over and over. So classical music, and I'm not always going to write the fraction for you, but just for the first few here. Classical is 5 over all is 40, which simplifies to 1/8, which equals 0.125. I'm going to 3 decimal places here because it's exact. I don't want to estimate if I don't have to, which is 12.5%. And then the relative frequency for country is 8 over 40, which is 1/5, or 0.2, or 20%. And again, you can simplify that fraction in your calculator if you'd like. Some of them you should be able to do by memory, doing it from your head. But you will have your calculator. I'm never going to tell you that this is a problem you cannot use your calculator for. So let's look at a couple more examples. A student conducts a probability experiment by tossing 3 coins, one after the other. Using the results below, what is the probability that exactly 2 heads will occur in the next 3 throws? Okay, so here are our results, and we want to know what is the probability of 2 heads. Not up to 2 heads, not 1 or 2 heads, but exactly 2 heads. So if we're looking at heads here, there's 3 heads, 2 heads, 1, 2, 2, 1, 0, 1. So how many of these have 2 heads? This one, and this one. So we want to know the numbers that have 2 heads over all. Well, how many tosses were there? I have to add up all of these frequencies in order to know how many tosses there were. So the probability of 2 heads, that's 7 plus 6 plus 2. And how many total are there? That's 5 plus 7 plus 9 plus 6 plus 2 plus 9, 10, and 2. Add all of those up. You should get 15 over 50. Simplifies to 3/10, which is exactly 0.3 or 30%. In the next example, similarly, this is an experiment, but this is done for a spinner. Using the results in the frequency table, what is the probability of the spinner pointing at 4 on the next spin? So a spinner is one of these. It's got an arrow 1, 2, 3, 4. That's a spinner. Okay, so we want to know what is the probability of 4. How many were 4? 18. How many were there total? 18 plus 21 plus 32 plus 29. If I add all of those together, we get 100. So 18 over 100 is 0.18, which is 18%. And I should simplify this as well, is 9 over 50. Always simplify your fractions if it can be simplified. Okay? So that's frequency tables, and we can use frequency tables to determine probabilities. Okay? The probability distribution remember, that was our second key term in our objective that we need to understand. A probability distribution shows the probability of each possible outcome. Okay, so if I were to find the probability of spinning a 1, a 2, a 3, and a 4, and I put another column here, that would be the probability distribution. And that's exactly what we're going to do here. Okay, there were 50 archers. Each archer shot 6 arrows at a target. What is the probability distribution for the number of bullseyes each archer hit? Okay, so frequency, we should add all of these up to get our total. And because of the way that the problem is worded, we should know that there should be 50 archers. So 3 plus 5 plus 7 plus 7, 11, 10, and 7. I double checked. Yes, it does add up to 50. The probability now is going to be how many of them hit 0 bullseyes overall. So that's 3 over 50, which does not simplify. 5 over 50, which does. 7 over 50, which does not. And so we keep on going and simplify whenever you can. And that is the probability distribution. So it's just taking that frequency table and filling in a new probability column. Let's take a look at the next page. All right, so the next page takes us into 13.3, where we'll be talking about permutations and combinations. Now, these are special ways of calculating probabilities and counting how many ways something can happen. Okay, so our objective is to use permutations and combinations in order to solve problems. And when we're using permutations and combinations, usually we're just talking about counting how many ways something can happen. We can then use that for probability. But we're going to focus first on just how to use them. So these answers are not always going to be probabilities. So consider, in a scenario where you're choosing an outfit, you can select from blue jeans or black pants, and you can select a red, a green, or a blue shirt. How many possible outfits can you choose? So you've got 2 pairs of pants and you've got 3 shirts, right? So you've got pants 1, pants 2, shirt 1, shirt 2, and shirt 3. So how many outfits can you make? Well, you can pair pants 1 with shirt 1, with shirt 2, or with shirt 3. And then you can wear the second pair of pants with any of the shirts as well. And so we have 1, 2, 3, 4, 5, 6 outfits. Well, what's another way that we can count this without having to write out all of those options? Because what if I had 5 pairs of pants? Then this becomes a lot more tedious to write out. Well, the shortcut is for each pair of pants, I can pair it with the shirt. And so for each means it's going to be a multiplication. So I have pants times shirts, 2 pants times 3 shirts give me 6 outfits. Okay, and we call this the fundamental counting principle. So if event M occurs in M ways, so if I have M options to choose from, and event N occurs in N ways, and I have another set of options to also choose from, then we can choose those two things together in M times N ways. So what does that mean? And again, my diagrams didn't print, so let me pause the video real quick and draw this diagram off camera. So we want to make a lunch, and we have options. We can choose a sandwich, a side, and a drink. And we want to know how many different options do we have? How many different lunch specials are possible? Okay, so we are choosing a sandwich, a side, and a drink. So that's really 3 choices. Our first choice is the sandwich. I think I spelled sandwich wrong. Sandwiches. Our rule is that we're multiplying. So then we have sides, and the rule is to multiply by drinks. Now, why are we multiplying? Because I can take ham and turkey with chips and juice, ham and turkey with chips and iced tea, ham and turkey with chips and lemonade. So for every option of ham and turkey, I have all of the options for drinks and all of the options for sides. And that's what multiplication does. Okay, so how many sandwiches do I have to choose from? 2, 4, 6 sandwiches to choose from, 4 sides to choose from, and 5 drinks to choose from. And so we get 6 times 4 times 5, which is 120 lunch special options. Okay, so let's look at one of these special ways of counting now, permutations. A permutation is when we're trying to say how many ways can how many outcomes can I have, how many options are there, in which the order of the objects is important. So think about first place, second place, third place, the order is important. If I get first place, it's different than if I get third place. However, if I'm mixing a salad, if I put the tomatoes and then the onions and then the olives, it's still the same salad as if I had put the tomatoes last. Okay, so a permutation is when changing the order of something changes the outcome. So how many different ways are there to choose the first person if you have 4 friends you're choosing from? So if there are 4 people here, how many options do I have for the first person? Well, I have 4 options. Now I've chosen a person. So now how many options do I have? Well, now there are 3 options left to choose from. I chose someone. Now there are 2 options left. And now there's only 1 option left. And so I had to make 4 decisions, but they were not the same number. Every time I made a decision, it went down. And so the way we calculate this is we say, well, my first decision, I have 4 choices, and then 3, and then 2, and then 1. And so 4 times 3 times 2 times 1 is 24. Now this special way of multiplying where it's decreasing by 1 for each choice that I make is called a factorial. And we write it with an exclamation point. So I had 4 friends to choose from. I know that it's going to decrease by 1 for every decision I make. And so it's 4 exclamation point or 4 factorial. And in your calculator, if you have a graphing calculator, the TI-84 is suggested, you're going to go into the math menu, and we'll go through this during class, over to the probability menu, and option 4 is that exclamation point. Okay, so I'll show you quickly, and then we will also do this in class together. So you're going to go math, over to probability, down to option 4. So if I wanted to do 4 factorial, 4 math, Probability option 4 is 24. Let's take a look at the next page. So this is a more formal definition of factorial. Factorial is when I take a number, n, and I multiply it by all of the numbers that are smaller than it. So n minus 1, n minus 2. So let's say if this was 8, factorial would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And we stop at 1 because if we were to multiply it by 0, that would be 0. And I'm not going to get to a point where I have 0 options left. Okay? So let's look at some examples. You download 8 songs on your music player. If you play the songs using the random shuffle option, how many different ways can the sequence of songs be played? Okay, so there are 8 songs and I'm going to shuffle them. So my first song, I have 8 options for my first song. And now I've already played that song, so now I have 7 options for the second song. And you see how this pattern is going to go? 6, 5, 4, 3, 2, 1. And so we can write this as 8 factorial. Now you can type it into your calculator as 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Or you can use the method I just showed you in the video. 8 factorial is 40,320. Let's look at the next example. In how many ways can you arrange 12 books on a shelf? So this is the same idea. We have a bookshelf. We have 12 options for which book's going to go first, and then 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Or I can say, I know it's going to decrease by 1 every choice I make. So that's 12 factorial. Now this one is even longer to type in if you type it the long multiplication way, or you can use the method that we showed you on the calculator, 12 factorial, 479,001,600. Make sure that you can get this number. If you're getting a different number, then that's something that we need to make sure to go over in class until you have a comfortable familiarity with how to calculate these. Okay, so now suppose, similar to example 1, we have 8 songs and we want to shuffle them, but I only want to play 3 songs. Then how many different ways are there to choose these songs? Well, I still have 8 options for the first song, 7 for the second song, and 6 for the third song, but then I'm going to stop because there isn't a 4th song. I'm not playing the 4th song, okay? And so for this one, we have 8 times 7 times 6, and then we stop. There were only 3 choices to be made. First song, second song, third song, and then we stop. And so we get 8 times 7 times 6, which is 336. Notice this is different than 8 factorial. 8 factorial multiplies all the way down to 1. This one stops after 3 songs. So how do I calculate this permutation? So let's look at some of this notation. Now, this is a special type of notation, and this is how it will be in your calculator as well. So if I wanted to calculate a permutation where I'm not using all 8, I'm only using a certain number of them, then we have this little r that denotes how many are we going to use. So we had 8 songs, we randomized them where the order mattered, and we chose 3 songs to play. So this is 8 permute 3. Okay, and what this does is it says 8 times 7 times 6, and if we look at it in terms of the factorial, times 5, 4, 3, 2, 1, but then we divided by all of the ones that we didn't use. We didn't use song 4 and on, so divided by 4, 3, 2, 3, 2, and 1, so that those cancel out. So we're left with just three numbers that we multiplied together. Now, how do you do this on your calculator? Very similar to the factorial. You're going to go into math, over to probability, and down to option 2. So this is math, probability, option 2, which is NPR, or permutation. Okay, so right out the previous problem, I kind of wrote it in the previous problem, but 8 CDs, choose 3 in order, is 8. The order matters, so it's a P, 3, and you'll understand what I mean by that in a minute. And 8 permute 3 is 336. Let's take a look at the next page. So when we were looking at the last examples, I kept reiterating that the order mattered. What if the order doesn't matter? If the order doesn't matter, then it's called a combination. So a combination is a selection of items in which the order is not important. So what's an example? An example is if I'm making a committee of 3 people, then it doesn't matter if you were the first on the committee or the third on the committee, you are on the committee. Okay? Another example would be if I'm for example, if I am mixing paint and I choose to make orange, right? Red and yellow make orange. It doesn't matter which one I put first. If I squeeze the red and then the yellow, or the yellow and then the red, it's still going to make orange, okay? So order is not important, then it is a combination. And the key word for combination is going to be that we are choosing, okay? So the key word here is choose. Now, if it uses the word choose, that does not mean it's a combination, okay? But when we read a combination, we're going to use choose for the C. So similar to the last equation that we saw with NPR, NCR is the total number of options that we have, and we are choosing how many of them, okay? The choose calculation in your calculator is right next to permute and factorial. So we're going math, over to probability, enter, whoops, math, over to probability, down to combination or choose, enter. So this is math, probability, 3 is for NCR, okay? So a yogurt shop allows you to choose any 3 of the 8 possible mix-ins for a smoothie. How many different smoothies are possible? Doesn't matter if I chose it first, second, or third. It's going into a smoothie. They're all getting mixed together. So the order does not matter. And therefore, I'm going to use choose. How many options do I have? 8 options. How many can I choose? 3 of them. And so we get 8 choose 3. And so we're going to do 8 math, probability, choose 3. And that is 56. Now you'll notice this is a much smaller number than when we did 8P3, right? We just did 8P3 was 336, 8 choose 3 was 56. Why is that? Well, if I choose 3 things, in a combination, it doesn't matter what order they're in. So 2, 1, 3, 3, 1, 2, 1, 3, 2. All of these are the same choice for a combination. For a permutation, these are all different. And therefore, for every choice that I make, a permutation has more options than a combination. So combination will be smaller numbers, okay? What I'd like you to do, if you have time left, is take a look at these 6 problems, and we will go through them together during our class right now. But if you have less than 20 minutes left before class starts, then you can just wait and we'll go through these together. Okay? So if you have time, take a look at these. If not, we'll go through them together during the very first part of our next class in just a few minutes.